So, we have come to a situation where the problem is that from the population we draw a certain number of samples, say n samples, and a part of that will be found to have the value of 1, a part of that will have the value of 0. And we are trying to find out what proportion has the value of 1. So, we have drawn n samples. Suppose the number of ones in that n sample is called x. So, x, the number of ones in the sample of n individuals. So, x is a fraction of n, and we will now face the problem of finding what is the mean of x, the standard deviation of x, and so on and so forth. If I draw that n number of samples again and again from that population, I will not get the same value of x every time. I will get different values, and those values of x will also have a distribution, and we have just concluded that if the number of samples becomes large, that distribution will become more or less a normal distribution. And now we are facing the problem of finding what is the mean of x and what is the standard deviation of x. So, our problem is the mean of x and the standard deviation of x. Now, x is the number of ones in the population in the sample of n individuals. Therefore, in finding out what x is, what I am doing is that I am picking up each individual from the sample, and we are asking whether it is 1 or 0. Again I am taking the second individual, I am asking 1 or 0. This is the same as what we were doing earlier. That means, we are actually making a measurement of the y's. Each measurement is y, which can have two values 1 or 0, we have seen that earlier. So, x, the measurement of x is actually n measurements of y. So, it is nothing but y plus y plus y, that goes on n times. So, if that be so, we have already found out what is the mean of y, then the mean of x is nothing but the mean of y n times. So, then we can argue that the mean of x can be simply expressed as the mean of y plus the mean of y plus the mean of y n times. And we know what the mean of y is. We know that the mean of y is p, therefore, n times of p is n p. So, that should be the mean of x. Now, what will be the variance? I would argue that we would carry out the variance exactly in the same way. So, the variance of y, variance of x, so variance of x should be again each measurement of x is nothing but n measurement of y, and we know the variance in the measurement of y, and therefore, this is nothing but the n times the variance of y. Okay. and the variance of y we have already learned n, variance of y is p into 1 minus p. So, that should be the variance of x. So, we have a distribution whose the variance is known, therefore, the standard deviation would be square root of n p 1 minus p. Okay. Now, what are we actually trying to find out? We are actually trying to find out the proportion, the measured proportion is the number that we have found, x is the number that we have found divided by the total number of samples, that is the measured proportion. Let us call it measured, therefore, it is not the proportion out there. Let us call it with a hat, so that we know that we are talking about the measured proportion. The ones that we have measured using the number of n number of samples is p hat, and that will be the measured proportion. And if we do a large number of trials of taking n samples each time, we will get a distribution of the measured proportions. For one sampling, that means we have taken n samples, we have got a measured proportion. If we do that again, taking another n samples, we will get another value of this. A third time you will get another value of this. Ultimately, the p hat will have a distribution. What will be the mean of that distribution? What will be the mean of the distribution of the p hats? So, that will be let us call it mean of p hat. That will be the mean of x divided by n. Since the p is x by n, therefore, it will be this, and mean of x is something we know, n times p. So, n times p by n, therefore, it will be p. So, if I repeatedly make measurements each time taking n samples, I will get a distribution, and that distribution will have a mean, which is the proportion of the proportion out there in the population. So, that is a good thing that we can obtain the actual proportion by making repeated measurements every time taking n samples. And what will be the standard deviation? The standard deviation sigma of p hat, that will be the sigma of x divided by sigma of x divided by, there are n samples, n. Now, we know that sigma f of x was square root of n p 1 minus p, and here is n. Therefore, this comes to be square root of p 1 minus p by n. So, the conclusion is that if there is a proportion in the population out there, and I am trying to find it using a sampling process, I am drawing samples, n samples each time. If I repeat the process again and again, then every time I will measure a different value of the measured proportion p hat, and that will have a distribution, and that distribution will have a mean at the population mean p, and that mean p hat will have a distribution whose standard deviation will be this, a well defined number. Well, you might ask, what is the guarantee that this distribution will be a normal distribution? earlier our argument for rooting on a normal distribution was the central limit theorem. But here we cannot apply the central limit theorem because it is a different problem we are dealing with. So, how do we ensure that it will be a normal distribution? Now, it has been found that the question is legitimate. It has been found that well, it goes by a rule of thumb. It is not difficult to see that if the number of ones in the population is too small, it is like a dwindling population, something close to extinction. If that is so, then the distribution will not be a normal distribution. So, there are situations where it will not be a normal distribution. Therefore, we need to talk about under what condition we can expect more or less a normal distribution, and there is a rule of thumb for that. The rule of thumb is, this is rule of thumb, it is not a theorem, just people have tried out and found that it works. That is, if the probability P, and P is a probability of getting a 1 times the number of samples is greater than 10 and if the probability of the other one, that means 1 minus p times the number of samples that is also greater than 10, then the distribution of the measured p hat will be approximately normal. If it is normal, then we can apply all that we have learned about the normal distribution. That is a major advantage. But the caveat is that that is not applicable to all cases. For example, if in the example that we have taken, P was 60, 0.6. Sorry, I will do it right correctly. P was 0.6, 1 minus P was 0.4, and suppose we take 20 samples. N is equal to 20. Then it will become P times 20, which is P into N is equal to P into N will be 12 and 1 minus P into N will be 8. So, obviously, this is not bigger than 10, and therefore, in this collection the normal distribution will not apply. So, if you keep on drawing samples of 20s and expect P hat to be distributed in normal distribution, that will not work. You have to take more than 20 samples, okay? Then only the normal distribution will work. Before we end, let us quickly do an example. Consider the Mendel type experiment in which there are tall plants and short plants, and you have collected a sample of 50 and you have counted the number and you have found that 33 are tall, all right. So, your measured proportion is 33 by 50 is equal to 0.66. The question is, can you state that the actual proportion out there lies in the range 0.64 to 0.68? Can you say? So, actual P lies in this range. This is the problem. Okay? So, how do we attack this problem? We know the mean will be, we have calculated the mean, sample mean to be this, and we can calculate the sample standard deviation sigma p hat to be square root of p 1 minus p by n. Now, p we do not know, therefore, we substitute by whatever we have measured, which is this. So, it comes to be 0.66 times 1 minus 0.66 divided by the number of samples we have taken 50, okay? And that turns out to be 0.067, okay? Now, will this distribution be a normal distribution? Let us quickly check. P is 0.66. So, P into n is 0.66 times 50 is 33, and 1 minus P times n is equal to 17. So, both are bigger than 10. So, normal. Okay. Distribution is normal, that is good. So, if the distribution is normal, then we can picture the distribution something like this. And we know the mean will be at P and the standard deviation we have just calculated. Okay. The question was the probability of this. So, probability of P of the mean of P is not P hat, P is within 0.66 and 0.64, 0.2 is within 0.2 of the mean. This is what we are trying to calculate. So, P hat 0.66 minus 0.2 and plus 0.2. So, our statement is what is the probability that this is true. So, this is again sorry, I will write this P as capital P because it is probability. Probability of again like the earlier problems, we will reverse the argument. We will say P hat is within 0.2 of the mean of P. The distance between this and that is the same as distance between this and this. So, we have the same argument, and then we have to express that as a multiplier of the standard deviation, then we get the value of z. Okay. So, the z value z is the multiplier 0.2, 0. Sorry, 0.2 or 0.02, 0.02, sorry. 0.02 divided by the this is 0.067 and that turns out to be 0.3, z turns out 0.3. So, we are essentially saying that p hat is within 0.3 standard deviations of the mean. Now, if you now consult the z table and find out what is the, suppose 0.3 is somewhere here, 0.3 would be 0.6, 0.3 will be somewhere here maybe. So, if you find this area, then you will find that the area is 0.6179. So, this area we will subtract 0.5 from it. So, 0.6179 minus 0.5, thereby we get only this area times 2. That turns out to be 0.2358. So, that is the probability of having the actual, the proportion of the two populations out there to be in this range, is only this much, which means that I can state with only 23% confidence that the population will be in this range, It is a very low confidence that immediately tells us that we need to change our strategy, we need to do something else in order to increase the level of confidence for proportion measurements. I will stop here and continue in the next class.